Hi guys, today we're going to look at how to sketch cubic polynomials. Polynomials are graphs which contain a number of terms which all have whole number powers of x. For instance, the polynomial here is x cubed minus 9x squared plus 15x plus 25. And we're being asked to sketch this as a graph or a function for all possible values of x. That is, for x as an element of all the real numbers. So, the first stage in this solution is to determine the points which are going to be used in producing the graph. And the easiest and first point that we usually focus on is the y-intercept. The y-intercept can be obtained by substituting an x value of 0 into the function, and in this case we can see that the answer will simply be 25. However, it is important to set out the working so that in more complex questions we can get used to the correct method. So we simply list for y-intercept, let x equal 0. Using this function notation where the x value is substituted for any number, we replace x here with 0 in the brackets, and that notation means replace x wherever it appears on the right hand side in the expression with the same value 0. So writing this down, y equals f of 0, 0 cubed minus 9 times 0 squared plus 15 times 0 plus 25. I like to use brackets because that way if there are negative values being substituted it does not create ambiguous expressions. These zeros wipe out all the terms containing an x, leaving just the 25, so we have y equals 25. Therefore the y-intercept is x equals 0 and y equals 25. Well, that's the first stage. This piece of information is important, so we highlight it as a reference so that we can come back to it when we get to producing our graph. The next stage is to determine the x-intercepts. Now this involves several stages. As before, to determine the x-intercept, we substitute this time y equals 0. This leads to the equation y equals f of x, the same cubic expression, equals 0. Now this cubic equation needs to be factorized in order to easily solve it. And there are several methods to solve or factorize cubic expressions. None of them work all of the time. These questions are usually designed so that there are simple linear factors, that is, simple whole number values of x, which make this equation equal to 0. So the first thing that we do is we systematically try different values of x. By systematically I mean try x equals 1, then negative 1, then 2, then negative 2, then 3, then negative 3. And usually by the time we get to x equals negative 3, we will have discovered a value of x for which this expression equals 0. So, as I said, to factorize the cubic polynomial, we need to find a linear factor first. Systematically test whole number values for x to yield a y value of 0. Attempt number 1, as I mentioned before, is to try x equals 1. So we substitute 1 in for x as before using function notation. This gives us 1 cubed minus 9 times 1 squared plus 15 times 1 plus 25. Shortcutting that gives us 1 take away 9 plus 15 plus 25. We can see that it's not going to equal 0. In fact it equals 32. The fact that that is not equal to 0 means that x take away 1, notice that's x equals positive 1, and I'm saying x take away that value is not a linear factor. So the next one to try is x equals minus 1. Substituting minus 1 in, we see here the use of brackets avoids any problems with squaring negative numbers. This gives us negative 1 minus 9 minus 15 plus 25. Notice the same values as before, but the odd powers, x cubed and x, give us negative 1 and negative 15 compared to positive 1 and positive 15. Recognizing this pattern allows us to save some calculation effort when trying multiple values. We see that these values do add to 0 as required, and therefore -1 is a solution and therefore an x-intercept. But in order to obtain all the possible x-intercepts, we say therefore x plus 1 is a linear factor. Now here's where things get interesting. Using this linear factor, we can now determine what the other linear factors may be. There are several methods. A very common method is to divide x plus 1 into this cubic expression using long division polynomial style. Whilst this always works, it is long and takes a bit of effort, and there is a better way. The method I like to use is as follows. To fully factorize the cubic polynomial, first of all, we write down the function that we had originally. Then we write down x plus 1 as one of the linear factors, and we need to put in another factor here, a quadratic factor, which when multiplied by x plus 1 will give us the original cubic expression. Now we know that we have an x cubed, and we know that we have a 25, and these two values are the keys for getting the first value and the last value in our quadratic factor. Since we know that x times x squared is required to give us x cubed, and to get the 25 there's only one way to do it, 1 times 25. So these two numbers must multiply to the last term, and the first two must multiply to the first term, which leaves us the middle two terms. Now, having placed an x squared here with the 1, that would give us a multiplied out value of 1x squared. We notice that we require minus 9x squared, so at present it's not correct. To go from 1x squared to minus 9x squared, we will require a negative 10x squared, and that comes from this combination. Notice again the 1x squared and the minus 10x squared must add to the negative 9x squared. That's how we knew it was negative 10x squared. And from this, we look at what the middle term here must be, such that when multiplied by the x, gives us the minus 10x squared needed. And we can see that that has to be minus 10x. Hence, we now have the quadratic factor, which itself can be factorized into two separate linear factors. In this case, it's a perfect square, x minus 5, x minus 5. Since negative 5 and negative 5 add to negative 10, and they both multiply to positive 25. This expression now of three linear factors can be written down as x minus 5 all squared. If they were different, we would simply leave it in that form. Now coming back to the original target, or the original objective, that was to determine the x values for which this y value is 0. We must complete solving for the x-intercepts. So that was our original equation as we had over here, only we now replace the cubic expression with its fully factorized form. X plus 1, x minus 5 squared equals 0. And it's now easy to see that this is only true if either x plus 1 is 0 or x minus 5 is 0. In the instance where there were three different factors, we might have had a third equation here. Therefore, x equals negative 1 and positive 5. Now for a cubic expression, when we have a linear factor squared, that corresponds to a turning point on the x-axis. I'll talk more about that in a moment. Therefore, we list the x-intercepts as negative 1, 0 and 5, 0. Since this information is important for sketching the graph, we highlight it for easy reference later on. Now, many classes only focus on these points for graphing or sketching the cubic graph, and they ignore the turning points. I like to include all the information, turning points as well as points of inflection, so we'll continue the calculation here. If you don't need to do these other parts, you can stop and sketch from just this original information, and that's enough to get the general shape of the graph. So step 3, let's imagine you were asked to calculate the turning points, so we'll do that. Now, one of the key things about a turning point is that it is a case of what we call a stationary point. That means the turning point is zero gradient. So we let the gradient function f dashed x equals 0. This f dashed x is a function which is derived from the original function using differential calculus. Now, you may not have done this yet, so I'll talk you through it. There's our original function. The gradient function represented by f dashed x, or alternatively the notation dy over dx. dy dx is a notation that represents difference in y over difference in x, or change in y over x, or gradient. Again, f dashed x is the functional notation. Now, what we do, and this is the important part, is we take each of these separate terms, and we have 4 of them. We multiply each term by the power, in this case 3 times, goes out the front, and we reduce the power by 1. In this case 3 subtract 1 is 2. So the term derived from x cubed is 3x squared. Likewise, the term derived from 9x squared, or minus 9x squared, is we multiply the 9 by the 2 to give negative 18, and reduce the 2 by 1 to give x to the power of 1, which doesn't need to be shown. The 15x is like 15x to the power of 1, so multiplying by 1 just becomes 15. Reducing the power by 1 becomes x to the power of 0, which is itself equal to the number 1 and doesn't need to be shown. And this constant term is like 25x to the power of 0, so when we multiply by the 0, it disappears. This equals 0 comes from our original condition that the gradient must equal 0 in order to have a turning point. So this is the condition needed for the x values in order that the gradient be 0 and we have turning points. So this equation itself can be divided by 3, giving x squared minus 6x plus 5 is 0. Itself a quadratic equation which can be factorized by inspection. The two numbers adding to negative 6 and multiplying to positive 5. Either x minus 1 is 0 or x minus 5 is 0, giving us two possible values for x, 1 or 5. Now these are the values of x for which the gradient is 0, and therefore these are the values of x corresponding to the turning points, not the x-intercepts, the turning points. To determine the corresponding y value for each of these x values, we simply substitute them back into the original function. So, when x is 1, calculate the y value as f of 1. Substituting in as before, replacing the x with 1, we end up with these series of values, and you might notice that we've previously done this same calculation over here, and we got 32, so no surprise we get 32 once more. So that means there's a turning point when x is 1 and y is 32, because this is the point for which the gradient is 0. Highlight that for reference later. The second turning point corresponds to when x equals 5. So we substitute x equals 5 into the original function. In the same way as before, when we do this, and you might note that this calculation also appeared, actually it didn't appear earlier on, but I did mention that we'd have a turning point at x equals 5 because of the repeated factor x minus 5. Substituting this in, we notice that these values here do calculate out to be 0. That's 125 minus 9 times 25 plus 15 times 5 plus 25. I haven't shown the actual calculation in there, but you can verify that for yourself. And since it equals 0, that means the y value is 0 when x is 25, corresponding to a turning point. But also, as noted before, this is one of the x-intercepts, or in this case touches the x-axis. Highlight that for reference later. Now, cubic expressions are actually graphed as graphs which have a point of asymmetry halfway between the two turning points. So the midpoint of these two turning points turns out to be where the graph stops curving one way and starts curving the other, and that is what we call the point of inflection. And for a cubic expression, it's always possible to work out the point of inflection as the midpoint of the two turning points, provided there are two distinct turning points. However, from calculus, the condition needed for a for a point of inflection is that the second derivative, f double dashed x equals 0. And this is calculated in a similar manner to before. There is the original function. We calculate the first derivative as we did over here, and we get the first answer, or the same answer. Now the second derivative is the derivative of this value, or this function. So we multiply the 2 by the 3 to get 6, and reduce the x by a power of 1 to give 6x. We multiply the 18 by the power of 1 not shown to give just 18, and as before the constant term disappears, and the 0 comes from the condition needed that the second derivative is 0 for the point of inflection. Second derivative corresponds to the rate at which the curving of the graph is happening. And if it starts curving one way and stops curving the other, then the rate of curving is temporarily 0 at that point. Notice the alternative notation for second derivative is to use a d squared here and an x squared there. This gives the equation dividing by 6, x minus 3 equals 0, or x equals 3. And again, note that 3 is halfway between 1 and 5. As I mentioned before, it is the midpoint. Also halfway between 32 and 0 is the y value of 16. So we'd expect to get 16 when we substitute 3 back into the original function, which we now do to calculate the y value. Substituting 3 in gives us 27 minus 81 plus 45 plus 25, which as expected is 16. This means there's a point of inflection at 3, 16. So highlighting this information for graphing. And as I mentioned, note that the point of inflection 3, 16 is the midpoint of the two turning points. Halfway between 1 and 5 is 3, halfway between 32 and 0 is 16. This is always true for cubic expressions. Now we have 5 pieces of information: a y-intercept, x-intercepts, 1, 2 turning points, and a point of inflection. This information can now be used to sketch the graph of the cubic expression. So let's list that information separately. Sketch the points and the graph, the y-intercept, previously calculated, the 2 x-intercepts, previously calculated, the turning points, I've listed them both here together, previously calculated, and our point of inflection. And we need to sketch all of these on a set of axes. Get our graph space organized, and note that the y-intercept is a positive value and the x-intercepts are biased towards the positive x value, so we want to have most of the action up here with the y-axis somewhere on the left side and the x-axis somewhere towards the bottom to allow enough room for these points to be shown. So it's worth inspecting these values to get a feel for where you should place the y-axis and the x-axis. So I'll do that, and we note that we have most of our room up here where the points will have plenty of space to be shown. There was no point emphasizing the negative or the lower values since most of the values are positive. Now we haven't labelled the axes, so that's important. Label y and x, and now we'll start plotting the values. Starting with the y-intercept, we'll choose a point about 2/3 of the way up and place our point in there. Remember to show both x and y coordinates to avoid any loss of marks from your teacher. We note that we do go up to 32, so we're going to need some space up here to show a 32 value. That's why I don't place this point right at the top. Placing the x-intercepts in, -1, I would choose a point somewhere around here, and +5, correct scaling would have the point somewhere around here. I've placed the point so that it's roughly 5 times further from the y-axis as this is from the x-axis. Now, being a sketch graph, the scaling doesn't have to be perfect, it's not a plot, so we just have to get the points in about the right spot, as accurately as you can, but label them correctly. Now the turning points, 1, 32. Well, if that's -1, 1 would be around here, 32 will be up here somewhere. And there we have it. And the second turning point we've already got in place at 5, 0. Now we're after the point of inflection. As mentioned before, it's the midpoint between these two, so we'd expect it to be around there. And there we have it, 3, 16. And now we have a series of points that correspond to a curve which should pass through all of them, turn here, and then go upwards. So if we sketch smoothly, and a good idea to use a pencil, from here we move around, down, up again. Place arrows on both ends of the curve to indicate that we're sketching it for all the possible real number values. Check our turning point here and here. Now, if we place a grid over this, and at the moment I should note that apart from labeling the function y equals f of x, or possibly the whole cubic expression, we could write down the whole cubic expression. As it is, that's the question complete. But I'd like to point out an interesting symmetry here that will help you understand cubic graphs. If we look at this central point of inflection, the graph on the left of it is exactly the same shape but rotated 180 degrees about this central point compared to the graph on the right hand side. In other words, about a vertical line, the left and right hand sides are reflections, but one is upside down. Now we can see this symmetry if I place a grid over the top, and I've done that by placing a line through each of the turning points horizontally and vertically, as well as the point of inflection. And we see that these squares are all the same shape and size. Interestingly, if we move from 5 to -1, we see we have to move a distance of 6 units to the left before we hit the curve again. Because the graph has that symmetry, 6 units from the other turning point at the same height should intersect at a point which is 6 units across. So that point of intersection should correspond to 1 plus 6, or 7, and given it's the same height, 7, 32. So I'll label that point in as well. It's not required for the graph, however it does help us understand this nice symmetry that we see in all cubic functions. Well, that's all. I hope that you found this useful. It's worthwhile going over the video a few times if you need to review some of the calculation steps. I've shown more detail than you probably need to show if you're doing this yourself. However, if you did show all this detail, it would be very difficult for your teacher not to give you full marks. Please check out my other YouTube channels, that is Ask Mr. Physics and Ask Mr. Maths, and once again, I will put up the solution to any question either in maths and physics that you pose in the comments. Please subscribe and like if you found this useful. Thank you very much. I'll see you next time.